In the name of God. Hello and welcome to this session of software testing class. Excuse me for my delay in announcement. I have another course with the same topic, with the same title, and I have sent the message for the other group, and when I noticed, I forwarded the message for you. Unfortunately, by delay, I sent by delay, but I announced you in the last lecture, in the end of the last lecture, that I like to hold this session online, and I want to receive your opinions about previous lectures, and if you have problems with the previous concepts, you can ask me and I answer your questions. Do you have any question? Do you have any problem with the previous lecture or previous lectures? Do you have seen previous lectures? Do you have my sound? Are you hearing me? Okay. Okay. If you have not any question, I prefer to start the lecture, and let me record the session for everyone who absent in this class. Okay. In this lecture, I want to talk about the model-driven test design approach, or how we use this approach in practice. As I said in previous lectures, The purpose of this approach is to raise the level of abstraction and hide more and more details of code, of source code of the software. We want to extract some structures from software artifacts such as source code to raise the level of abstraction, and we should present a mathematical view of the internal structure of source code or software to design better test sets or better test cases. So in this approach, one test designer do the math. This means that a test designer should, as I said, should extract some structural models, such as control flow graph, such as data flow graph, and other mathematical representations for internal structures of the software, and do test generation by some way of test engineering. So in this lecture, for example, I explain how we extract a control flow graph and how we can use this structure to generate test cases, and how what coverage criteria could be defined for this structure, and how they are used to generating test cases. In this approach, so the test designer generate structural models, and traditional tester and programmers can do their parts, such as find values, find input values for test cases, automate the tests, and generate the test script so that they could be run automatically, run the test cases or test sets, and evaluate the result of the tests, which tests failed or which tests passed in our observation or examination. In this approach, like the traditional engineering models, but each are good for test generating. Deep traditional software engineer generate for design phase or in analysis of requirements. This model is more mathematical than normal models. Exactly explain how the program process is input. So in this approach, or techniques, we go ahead and explain how we can use this approach. The part says that test designers become technical experts who do the math, who expert in programming, who familiar with design methods of software product, and so on. In a model-driven test design approach, we start with a software artifact such as source code, a piece of code, the source code of a method, or a source code of an object or class. Its class. We start with this artifact as our base for test generation. By analyzing this artifact, the test engineer, the test designer should generate or extract some structures, some models from the source code or software artifact to design test cases. Excuse me. Of course, this is a method or class in a programming language. So probably you are familiar with how extract some structures from code from compiler course in undergraduate. Your undergraduate study. In this stage, we have a model that is specify how a program process its inputs and how statements of program change the state of the internal state of the program. Then from this structure, we can generate test requirements. As I explained for you in previous section, in previous lecture, the test requirement is a result of using a coverage criterion to generate the set of things or structures that could be covered by test cases. So with some test coverage criterion, with the help of some test coverage criterion, especially for the structure, defined for the structure, we can generate a set of our test requirements in criteria-based test design. But on the other hand, we can use the help of domain experts to define some other test requirements by human-based test design approach. And next, we should combine these sets and refine test requirements. So in this stage, we should define or generate test values. We should generate test cases to cover all of the test requirements if possible. As you know, some of the test requirements may be infeasible, such as test requirements related to dead codes in our programs. So if possible, we try to cover all of the refined test requirements by generating test values and test cases to examine the relative code of the test requirements. In this stage, we return to implementation abstraction level from design abstraction level by using the input values to generate actual outputs or actual results of the test by observing the behavior of the program with these input values. For have test cases, we should add some extra data to input values to form test cases. For observing the behavior of the software of a program for a special input, we need to set the state of the program in a situation which can run a special method, a specific method of the program. So we should do a prefix setting. In a prefix setting, we just change the state of the program to a specific state which can call the intended method, the method under test. As you know, for example, when you want to use a class, you should define some objects, some instantiations of that class in your program, in your main method of your program, and initialize or allocate memory to the defined object and initialize some internal variables of the object so that it could run its method. So in prefix values, we should define the needed values for initialization, the class. Moreover, in this stage, we should provide the expected result. What is the expected result for a specific input values? This means when we want to run a specific method with a specific input, what is the result that we are expected? The prefix values, the expected results should be added to input values to form test cases. In this stage, we have test cases that could be run over the program under test. Okay. In the next stage, we should generate test scripts so that it could run the tests, our test cases automatically. In this course and in next chapter, we teach how we can generate test scripts in, for example, JUnit platform for Java codes. So in the next session, we talk about the test scripts. If you have any problem with test scripts, please postpone your questions to the next lecture. This lecture just we define the approach, we explain the approach of model-driven test design. In the next stage, we should execute the tests over the program and the test, and record the results, the actual results of the test cases. And in the next stage and final stage, we should evaluate each test case. We should compare the expected result of a specific test case with its actual result that we are received in a previous stage by execution of the test case. So in this test case, we could find out which tests are passed or which are failed. Okay. So as I explained for you, in the first stage we should do some analysis tasks to extract structures from source code, and we should do some domain analysis to define some test requirements by expert users, by domain experts, and by the help of some coverage criterion, we could generate test requirements from model structure, and the refinement should be done to have a unique set of test requirements. And in the next stage, as I said, we should generate test cases for covering all of these test requirements. And as I explained for you, in this stage we should add prefix values, postfix values, and expected results to the input values to form test cases. So as you know, as I explained in previous lectures, a test case is a multi-part artifact. Is an artifact that forms from 4 parts, includes 4 parts. The first part and the most important part of the test case is the input values, test data. It's test data. The next one is prefixes. I explained this concept for you just a moment before. But what about the postfix? When we want to run some some methods of our program, as I said, we should set the state of the program into an appropriate situation in which the program, in which the object could run the intended method. But when the test case is run, after running the test case, we should return to the previous situation. We should return to the situation before executing the test case. As you know, execution of a test case could change the state of the program. So we should return the program to the situation just before execution of test case. This could be done by postfix values. In this part of the test case, we define some values for some internal value that reset the internal state to the T state of just before executing of the test case. The expected result is explained for you before, and there is no problem about this concept. In automate phase, we should, as I said, we should generate test script to run test cases automatically, and in the next state we observe the behavior of the program for a specific test case, and we receive the test results or actual result, and I can evaluate evaluate the results in the last stage, and the results of this activity in this level should be returned to other people of the team, especially for managers, test designers, or for developer team, and some other people such as users should be noticed from the feedback of the test, from the results of the tests. So if you have any question, you can ask your questions about this approach. In the next slide, we explain this approach more clearly by an example. But if you have any question, you can ask your questions. Do you hear my song? There are two messages. There's no sound. Yes. Do you have any question? No question. So let me explain how we can use this approach in practice. In this slide, the four activities that I explained in previous lectures in software testing are stated. In this stage, we just do a test design. Actually, in test design, the output of the test design phase is some input or test data. So in this phase or in this activity, we should generate our test data for our test cases. We should generate our prefix, the prefix of our test cases, the postfix, and expected result. After this stage, we have some test cases grouped in test set. In this stage, we done the test automation activity, and next one is test execution, as you know, and the final activity is test evaluation, as I explained in the previous slide. As you see, this approach rises the abstraction level, which make test design much easier. Why? Why much easier? Because I do not work with details of source code. We just work with some models, some abstract models which hide the details of the code and drive the abstraction level. And obviously, we do test design more simpler. And how we can use this approach for generating test data or doing test design activity. In this example, you can see a Java method, a simple Java method, which returns the index of the element n in an integer array A. This is a sequential search method, simply, which states the index of element n in array A. For this, as you know, we should scan the elements of array one by one until we find the element n. And if the n is not located in the array, ultimately we should return -1. For this, we use a for loop which scans the elements from 0, 1 from index 0 from the beginning of the array to the last one. When we find n in the array, we should return the index of n. This is a very simple method, and I want to explain you how we can do this approach for generating test cases, and how criteria could be used for generate test requirements, how test automation should be done, how test execution should be done, and etc. Excuse me. One of the structures you can extract from code, as you know from compiler course and other courses in your undergraduate stage, you know that a control flow graph is a suitable structure for analyzing or illustrating internal structures of the source code of a method. So in this case, we can extract a control flow graph from this code. Suppose in the first stage, in the start of the execution of this method, we be in location 1 or in state 1. In state 1, we have a counter I for the loop for which initialized by 0. In the next statement, if I is less than the size of array, we could execute the if statement. So in the next state of our control flow graph, we should compare I with the size of the array. If I is less than the size of array, or if there is another element in the array, we could test or compare that element with the value of n by if statement. So we can go to this state of the control flow graph, and if statement executes. In this state, if the element n was found, we can return the index of n, the index I, the value of I as index of element n. If not, we can return to the loop by the next element, and we run loop for the next element to to compare again n with the next element, and so on. we do this loop while the element n is found in this loop, or we reach the last element and don't find the element in the array, we go to the final state 5 and we should return -1. This is a control flow graph. This is a simple control flow graph which explains, which illustrates the internal structure of this method. In the next stage of the test design process, we don't need this method. We don't use this piece of code. So we just use this structure to design test cases. But for design test cases, we need some extra tools more than this structure, which one of them is a coverage criterion. Which coverage criteria could be used for test generation from control flow graph. Some coverage criteria for graph structures, as I will explain in chapter 7. Some of them include node coverage, edge coverage, edge pair coverage, or for example, path coverage. These are some criterion for graph structures. In this chapter, we use edge coverage, for example, and edge pair coverage to generate test requirements. If we use edge coverage, we should design test cases that examine all edges of this structure. Okay. If we choose edge coverage as our coverage criterion, we have test requirements set that include all edges of the control flow graph. As you know, all edges of control flow graph are the edge from state 1 to state 2, state 1 to state 2, and state 2 to state 3, state 2 to state 3, and then state 3 to state 2 again. This edge. Each pair of these values show a specific edge of the control flow graph. So if our coverage criteria is edge coverage, we should cover all edges of this control flow graph that is equal to this set of edges. We should cover all of these edges to satisfy this coverage criterion, to fully cover this coverage criterion. On the other hand, we can use another or other coverage criteria to design test cases. For example, if we use edge pair coverage, we should extract all edge pairs from this control flow graph as our test requirements. So note that our coverage criterion is edge pair coverage, and our test requirements for this criterion which consists of, which includes the set of H pairs. Of the flow graph of the first H pair is the H pair which starts from state 1 and lead to state 2 and connect to state 3. For designing test values, we should define how many passes should be executed to cover all of these H pairs or to cover all of these edges. So you can check that these 3 execution passes from this structure could cover all of the H pairs. For example, if we run this pass, we execute the method for this pass, which start from state 1 and go to state 2 and go to state 5. Can cover an H pair and this H pair, which is this H pair, the second H pair. And if we run the method for this pass, if we run the method for this pass, we could cover some other H pairs. We could note that in this pass we go from state 1 to state 2 and from state 2 to state 3 and from state 3 to state 2 again, and then we go to state 5. So by this execution, we can experience the H pair that connect state 1 to state 2 and state 2 to state 3. 1, 2, 3. These H pairs could be covered by the execution of this pass. And the next H pair that covered by this pass is the H pair that connect to state 3 to state 2 again. This H pair is covered. This H pair could be covered again by this execution pass. And the last H pair that could be covered by this execution pass is the H pair that connect state 3 to state 2 and state 2 to state 5. This means this execution pass and these H pairs, the H pair that start from state 3, go to state 2 and then go to state 5. So by these 2 test passes, we could cover some of these H pairs, but not all of them. As you notice, this test pass, this simple test pass, just cover the second H pair. This H another test pass, another execution pass by this structure, so that it should cover these two edge pairs. For cover the third edge pair, we should define a path that connect state 2 to state 3 to state 4, state 2 to state 3 to state 4. So the next test path should be include these subpaths. The another subpath should be covered by the next path. Next test path is this edge pair. Start from state 3, connect to state 2. Excuse me, this state. Start from state 3, connect to state 1, then go to state 3. So if we run this test path, I could cover all of the edge pairs by these three test passes. Excuse me. Note that we want to pass this pass. We execute this. We want to execute this execution pass. So our array should be null or empty array. If we have an empty array, in the first check, we find that there is no element in the array. Just a test is that consists of an empty array with any value for n. The value of n, don't care. Not important. For the other test pass, for another test pass, the second test pass, which inputs are suitable? In this test pass, we should go from state 1 to state 2, state 2 to state 3, state 3 to state 2, and then go to the last state, the final state 5. This pass should be executed. By which input values this pass could be executed? This pass from 1 to state 2 to state 3 to state 2, and then go to the final state. When we can reach to this state? If I have an array which not include of element, reach this state. This state shows the element n is not located in array A. So the first thing that I use it to design our test case is that our test input for this task, our input array should not include the element n. The second thing is that this task just check, just execute the for loop one step, one bar. We have a one bar. Any value except n. So the next input value could be array with my connection was lost for a moment. Do you have my sound? Do you hear my sound?